Hello, and welcome to section 4.1 for Algebra 2. Today we're going to learn about polynomials, their graphs, some end behavior, and other things like that as we go through this. So first off, we want to talk about a polynomial. A polynomial is a monomial or the sum of monomials. Monomial means one. All right, or the sum of them. So remember, terms are separated by addition and subtraction signs, so it's a combination of them. All right, when we get into this, we're going to talk about polynomial function. A polynomial function is a function in the form, this thing. All it's basically telling you is that the leading coefficient goes with whatever the degree is, or the exponent. So if this was 3, our exponent would be 3. If this was 3, n was 3, this would be 2. It would be our coefficient for that. Where a sub n cannot equal 0. All right, it's just one of those things that you go through and you realize that if that's 0, then it makes a lot of other things. It changes the degree of the polynomial and everything like that. All right, so we have a couple things here we want to talk about. We start talking about a sub n. A sub n is the leading coefficient all right, I like to use an abbreviation which would be LC for leading coefficient. Okay, n is the degree. Okay, the degree is also the highest exponent, so I'm going to put that in parentheses. And our a sub 0 is just our constant. Okay, so that's just a couple things that we need to make sure we're okay with here, just to kind of start off talking about these. So when we talk about this, if we have something of degree 0, what that really is just a constant. All right, an example of a constant function would be 3. Right, it's just going to be a number. All right, if the degree is 1, the type would be linear. All right, just of this form, that's all it's really telling you. I just filled in the values here. Degree is 1, so that's 1, that's 0. Anything that's linear, 1/2 x plus 4. Okay, something the degree of 2 would be quadratic. Stuff we spent a lot of time on this year. We could have negative 2x squared plus x minus 5. Right? The examples here, I'm just making them up. It's just basically the important thing is our degree is correct and it goes with this thing in the front. Something to the third power is cubic. And our thing here just needs to be, I could just say 4x to the third. The degree is 3, so therefore it's cubic. 4 would be quartic. All right, and we just need something to the fourth power. How about negative x to the fourth plus x plus 13, okay? So those are just some examples. If we had something to the fifth power, I'll just put it here. All right, that would be quintic. All right, and the same thing here, our example would just be, I don't know, negative 3x to the fifth minus 1. Okay. The example, like I said, doesn't matter except for the degree, just showing you what it would look like. Okay. So now when we get into the next part, there's a couple things that make something not a polynomial. Okay. What causes something to not be a polynomial? The first thing would be a non-whole number exponent. All right, when we start talking about non-whole numbers, basically we can't have negative numbers or fractions, just to make sure we remember what a whole number is. Whole number is basically starting at 1, 2, 3, 4, so on and so forth. Okay, we cannot have a variable exponent. All right, and we cannot have a variable in the denominator. Okay, that kind of goes with a non-variable or non-whole number exponent, all right? But just want to make sure you realize if you ever have a variable in the denominator, it's not a polynomial because we'd have a negative exponent. That's something we'll get into in future sections. Okay, so the next part, they want us to decide whether the function is a polynomial. That's our first part. Our second part, we then need to write it in standard form. And once we write it in standard form, we're going to state the degree, the type, and the leading coefficient. Okay, so the first thing we always want to look for, is it a polynomial? We look here, negative x to the third minus 4x to the negative fourth. As soon as we see this negative 4 right here, we can say that this is not a polynomial. Right? Because the reason here would be the negative exponent, or to use the terms up here, it would be the non-whole number exponent. Okay? I sometimes will also abbreviate not a polynomial as NAP. All right? Okay. Example B. We have 0.5x squared plus the square root of 3. Notice the x to the fourth outside plus 19. All right, this is a polynomial, so we need to write it in standard form. We write it in standard form. We want the highest exponents first. Our highest exponent here is x to the fourth. Then we would have 0.5x squared plus 19. This is now standard form for this polynomial. We would then say, well, what is the degree? The degree is our highest exponent, so that's 4. All right, our type, well, if something's to the fourth power, that's quartic. And the leading coefficient is the number out in front, which would be the square root of 3. Okay, so that's example B. For example C, we want to do the same thing. We want to see if it's a polynomial as we go through. X squared plus 9x, 9 plus 9 to the x. So right now we can say once again, not a polynomial, no, or NAP. Okay, and our reason here is we have a variable exponent. All right. So if we look at our next page here, we have a couple more examples of these. All right. So we want to look, negative 4x to the fifth minus 7x squared minus 2. This is a polynomial because we don't have anything that makes it not a polynomial. And the nice part is this one is in standard form. So I'm just going to say in standard form. And now we would go through and say, well, our degree is our highest exponent, which is 5. Our type is that one I added in, which was quintic. And the leading coefficient in this case is negative 4. Okay, last example of this, we have q of x equals 2x to the fourth minus 8x squared minus 7 plus 5x. This one is a polynomial. It's not in standard form, so we'd have to write it in standard form. And the only thing we need to switch here is the 5x and the negative 7. So remember, we want our exponents going down from left to right and our constant at the end. Our degree is to the 4. There's a 4. So the type is quartic. And our leading coefficient in this case is 2 because it's a number out in front. All right. Now, for the next part, okay, we're going to start talking about something we call end behavior. End behavior of a function's graph is the behavior of the graph as x approaches positive infinity, all the way to infinity on the x-axis, or as x approaches negative infinity. Okay? End behavior is determined by the function's degree and sign of the leading coefficient. All right, so when we go through and talk about this, I'm going to ask you two main things. I'm going to say, is the degree odd or even? And is the leading coefficient positive or negative? All right. To make things a little bit easier, instead of having to say, as f of x approaches negative infinity, x approaches negative infinity, we're just always going to talk about from left to right. So if we went to negative infinity, this graph we would refer to as down up. So as we came from left to right, for an odd positive, it's down up. All right. As we come from left to right for an odd negative, we would describe this one as up, down. Okay, so those are our two odd degrees. Our two even degrees, well, this one would be up, up, and an even negative would be down, down. Okay, there's a couple main tricks when we talk about these, all right? I always remember, and this is just me, you guys find other ways to do it as well. If it's odd, they end in opposite directions, all right? And the right-hand arrow is always the sign of our leading coefficient. So if it's an odd positive, we know our right arrow goes up, and odd tells us it's opposite, so our other arrow would be down, all right? If the leading coefficient's negative, it ends down towards negative infinity, and it's odd, so it's opposite, so it's gonna be up, down, all right? Even they're always gonna be the same, all right? And once again, the right arrow always is the same as the leading coefficient. So if the right side's, if it's an even positive, it would be up, up, even negative, down, down, all right? So all we're gonna do for the next three examples here is just describe the end behavior of the graph. So for the end behavior, we need, well, what is our degree? So just be careful. Remember, they're not always going to be in standard form. These examples are, but I'll just say be careful. We always want to look for the degree, which is the highest exponent, and then our leading coefficient off of that. So in this case, our degree is 3, so that is odd. And our leading coefficient is negative. So that tells me my right-hand arrow is down, and it's odd, so they go in opposite direction. So my end behavior, or EB as I describe it, is up, down. For example B, we do the same thing. Well, what's our degree? Our degree here is 4. 4 is even. And our leading coefficient is this negative 5.5 here. So that's negative. So our end behavior is going to end down for our second arrow. And we know they're even, so they're the same. Our end behavior would be down, down. All right, example C, degree is 5, and 5 is an odd number. Leading coefficient is 3 here, which is positive. All right, so our end behavior, we know it's positive, so the right-hand side is going to end up. It's odd, so we would say down, up. All right, that's end behavior. Okay. All right, so now, obviously we have some other things we can use here. We have our graphing calculators, we have Desmos and things like this. But just to kind of show you guys how we could do this if we ever asked you to do this by hand, or just kind of sketch it quickly. So steps to graphing a polynomial. We want to plot points to determine the shape of the graph's middle portion. Good range, like -2 to 2-ish. Connect the points with a smooth continuous curve, and then use what we know about end behavior to sketch a graph. All right, so I already got these values here. -2 here is 6, -1 is 6, 0 is 2, which is the y-intercept, 1 is 0, and 2 is 6. So these are just something I already got here. So I'm going to plot these points. All right, And now the other part that can help me here with my graph is, well, what's the end behavior? All right, if we look at the end behavior, this is an odd positive. So if it's an odd positive, right, those are the two things we need to know. My right arrow ends up, and odd is opposite. So my end behavior is going to be down, up. So when I now go to graph this, I know my graph's going to have to come from negative infinity somewhere down here, up, and end towards positive infinity here. I kind of missed that line, but you guys kind of get what you can do here. All right, obviously graphing utilities will help us get the real shape of them, but we just know we can get some points and go from there. All right, our next one, all right, well, same thing, I have these points already figured out. -1, 0, -3, -4, -21. All right, so -2, -1, -1, 0, 0, -3, 1, -4, and 2 is going to be way off the graph down here. Okay, so when we go to graph this one, we know our degree is 4, so that's going to be an even. And then this thing out in front here is negative, so it's an even negative. So our right-hand arrow is going to end towards negative infinity. It's even, so it tells me they're the same. We have down, down. All right, so I kind of know my graph's going to end down here. This is -21, so I know it's going to end way down here anyways. Okay, and then I kind of just figure out the shape of the rest of the graph. All right, the important thing is here is that you get the end behavior, and you can kind of just plot some points in the middle to get a graph, picture of what the graph actually looks like. Okay, 2 more examples and we're done for today. Okay, so now what we're going to do is we're going to sketch a graph given the characteristics of these graphs. All right, so they're going to tell us when the function is increasing, when it's decreasing, when it's greater than 0, and when it's less than 0. I have a couple steps here. If you guys have highlighters, I think highlighters will really help here. All right, so what we're going to do here is we're going to start with the zeros. Okay, well, how do we know what the zeros are here? Well, our function's greater than 0 when x is greater than -4. Ooh, that number's the same, 0 and 5. So we're going to plot -4, 0, and 5. Those are our zeros. So we're going to start by plotting those. All right, so now what I'm going to do next is use a highlighter. All right, so when my function is greater than 0, I'm going to use the yellow highlighter. Well, my function is greater than 0 when x is greater than -4. All right, well, where is that? Well, that's everywhere over here. So I'm going to highlight this whole region of everything less than -4. All right, it also tells me, and it's between 0 and 5. So I'm going to highlight this as well. All right, it will obviously keep going too in different aspects, but just in this case, we kind of can tell. All right, and now I'm going to highlight when my graph is less than 0, well, between -4 and 0. All right, and when x is greater than 5. This just kind of gives us an idea where the graph is going to be located. All right, so now what I'm going to do is just look at my next values here. The only other 2 values I have at the top, right, and I'll even say here, use increasing and decreasing points. All right, these are basically going to be our turning points Well, we have -2. So if I went to my graph where x is -2, I need to put a point somewhere here in this highlighted region. Doesn't matter where, on -2. Tell me when to stop. Stop. So I put that point there. And my other point is 3. If I look at 3, 1, 2, 3, now it's going to be in the top part, and then tell me when to stop. Stop. Okay, doesn't matter as long as it's on 3 in the highlighted region. Okay, so now what I'm going to do is just connect my points, right? I have to come from this point here in the highlighted region, kind of come down, boop back up. And there's something that be a sketch of my graph that fits these characteristics. The only other thing I could now say, well, if we talk about our end behavior here, our end behavior is going to be up, down. So from my graph, what I've done here, and knowing my end behavior, I can tell that this function is now going to be an odd negative. Our degree will be odd, and the leading coefficient will be negative. All right, so it's kind of interesting how it all kind of comes together. All right, one last one, and we'll be done for today. All right, so once again, we want to start with our zeros. Well, where are our zeros here? Our zeros are at -2, 3, and 5. All right. So remember, these here are our zeros, right? That's where we want to start. All right, so now we take our highlighter, and now we're going to say, well, our function is greater than 0 between -2 and 3. And when x is greater than 5. All right. And now we would go through and say, well, when is it less than 0? It's less than 0 when x is less than -2. All right, so everywhere over in here. All right, between 3 and 5. Okay. All right, and now we go with our increasing and decreasing. We have 0 and 4. Well, where is x 0? Here. Well, 0 in the highlighted region, somewhere in this point here. Doesn't matter where, as long as it's on 0 in the highlighted area. And 4. 1, 2, 3, 4. Highlighted area, somewhere in here. Right, stay in the highlighted region. Kind of come up, loop down, right, whoosh, and then back up. All right, so I stayed in the highlighted regions, hit the points they needed me to do, and I'm good. So my end behavior with this one would be down, up, right? Down, up. So this is going to tell me that it's going to be an odd positive. All right. So this is your video for section 4.1. Your homework will be posted shortly. If you have any questions, please let us know. Have a great day.